rule. Product rule we talked about yesterday, and we said that if we have a product, let's write it down. If we have y equals ub, then y prime equals what? ub prime plus v prime. Good. Okay, so there's our product rule for derivatives. What does that do for us here?
5x.
Okay. And the derivative, oh yeah, we don't know that one, do we? Whoops. Sorry, that's a bad one. Let me change that a little bit. Sorry, that's for today. I'll do that one today, but we haven't done it yet.
Yeah,
got a little carried away there.
It's just so much.
I'm gonna make it cosine.
Wait, what did it been secant then?
No, it's not. Yeah, it's not.
Well, if it's 1 over.
Okay, so make it a cosine. Now what do we do?
Sine.
Okay, good. Derivative cosine. Say it again. Negative sine. Okay. Plus. Okay, plus cosine x times 5. Okay. And then we could just simplify that. Now, that works. Is there anything we could have done there that would have made that at all simpler? And I know that you're going to think I'm just so nitpicky here after a while, but this is what calculus is largely about. It's just making things, being as systematic and strategic as we can. Because later on, things get bigger and harder. Any other? Okay, cool. Maybe here, what might have been a good idea would have been to just pull that 5 out front and make our product a little bit smaller. Right? It doesn't change things dramatically in this case. But what we would have ended up with then is the 5 out front. And just that, right? Not a big deal in this case. And so if we get it all cleaned up then, let's see, what do we get if we get that all cleaned up here? And here's another issue that's just minor, but we got to start getting used to, is how do we write a simplified version of that answer? For one thing, we always want to have the constants, even if we redistribute this 5, and so I've got the 5s in both terms, which is fine. You always want to put the constants first. So I'm going to have the 5 out front, then you want the variables, and then after that you put the trig functions. And here's why. It's a little bit confusing. If I were to say something like this, what if I said negative 5 sine x, x? That's a little awkward, isn't it? Because I've got those two variables next to each other. It forces me to maybe do something like that. And so we want to make this as unambiguous as possible. So we'd rather stick that variable out front. Okay. And write this as negative 5x sine x plus 5 cosine x. Or what I would even do, what I always tend to do, and this is just probably a personal bias, if I've got a negative term, I always like to put the positive terms first. And then you have to write, this is really nitpicky, but then you have to write one fewer operations. Notice that if I do that, if I put the 5 cosine x first, I don't even have to write the plus sign there. And it might seem like a lot, so that's not a big deal, but it's just, I mean, I just always just do that without thinking about it now. It's just something that just makes things a little bit simpler. And then it also looks like a difference of terms, more obviously. And so in some cases, we might end up multiplying by the conjugate or something like that. So it kind of sets you up for the algebra just a little bit better. I mean, that's minor, but does that make sense? Okay. All right, I'm going to show you a new trick here. I'm not going to prove this one like I did yesterday. I'm just going to give this one to you. Proof would be similar to what we did yesterday. The quotient rule. And so if we do, I'm just going to go ahead and write this one in terms of u's and v's. You'll see it in the book written in terms of f of x and g of x, but it just looks really complicated if you do it that way. So let's just write it in terms of u's and v's. The derivative with respect to x of u divided by v, we have quotient rule here, is equal to v u prime minus u v prime divided by d squared. Okay. Considerably more complicated than the product rule. And there's something about this one that makes it actually quite a bit more tedious, and prone to mistake prone. If we compare this to the product rule, notice for one thing that the order of the terms does not matter because they're both positive. It wouldn't be a big deal at all if we wrote the VU prime first in the product rule, would it? Makes no difference. If addition is commutative, right? If I'm adding things up, I can add them anywhere I want to. But that's not the case with the product rule. The first term is positive, but I'm subtracting the second term, and subtraction is not commutative. We know that 3 minus 7 is not equal to 7 minus 3, right? And so you got to get this one right. You got to really remember this one. Now, there's a couple ways you can think of this. You can think of it in terms of top and bottom. The derivative of a quotient equals, you start on the bottom. Think about that. Equals bottom times derivative of the top minus top times derivative of the bottom over bottom squared. So you start on the bottom. B comes first. The other way I sometimes think about this is if we define u prime as du dx and v prime as dv dx, then it's like you're saying video in the first, when you say the quotient rule. It's v du dx minus u dv dx. If we write u prime like that, and v prime like that, it's like you're saying video, v du dx minus u dv dx. But start on the bottom, video, however you want to remember it, or just remember it that way. Just remember the formula. You got to start with the v. Okay? Now let's try one of those. Let's try, how about, let's take one out of the book here. How about this? Okay, there's an example of a problem that we could not have done before this section. Well, we couldn't have simplified that in a way where we could have used power rules and stuff. We got to use quotient rule on this one. Okay. So there's our quotient rule. What do we do with this? What's our u and what's our v in this case? Okay, good. So what does the quotient rule tell us then? Well, almost. We gotta do a little calculus here. We have to do some differentiating. But what's the pattern predict force then? In the numerator of this quotient rule, what are we gonna get? Okay, we get the quantity x squared plus 1 times 5. Okay, the derivative of the top, and the derivative of 5x minus 2 is just 5, right? So there's our derivative minus 5x minus 2 times, someone said it, derivative of the bottom would be derivative of x squared plus 1 would just be 2x. Good. All divided by x squared plus 1 quantity squared. Good. Okay, so there's the calculus, and as happens so often, you'll see this pattern repeated again and again. The calculus is pretty easy. Now it's just a matter of doing a bunch of algebra to make that look okay. So what's our algebra look like? Okay, good. Distribute 5, so I'm getting 5x squared minus 5. If I distribute the negative 2x here, minus oh, did I mess that up?
Yeah.
Oh, plus pi, whoops. Sorry. Thanks. Okay, what next?
-10.
Okay, minus, and I'm gonna get 2x times 5x is good, 10x squared. Okay, and if we count the signs here, I got a negative times a negative, so it's positive. 4x, good. All over x squared plus 1 squared, and so I guess we collect like terms. What do we get? Negative 5x squared plus 4x plus 5 over x plus 1 quantity squared. Sound good? Okay. And that doesn't look super pretty, but that's the answer. That's what we get. That's our derivative function. Question?
Could simplify it if you like, because you
Forgot
forgot
that
about square
square
root back to the
bottom
bottom.
of the x.
Whoops, I'm forgetting lots of stuff. That one, I don't think that one's gonna factor. And we can kind of, you mean, could I factor something out at the top and cancel? Is that
Well,
the
yeah,
suggestion?
if you like distribute the square, and then.
Well, okay, but I can't distribute the square. I'd have to FOIL this thing
Yeah,
out.
okay.
Yeah.
Foil that, anything.
But the problem is, x squared plus 1, does that factor?
Do that.
Well, in fact, would it be even different than that? Is there a pattern? We have a pattern for difference of squares, right? But is there a pattern for a sum of square? No. Sum of squares could never factor. And so, and let's just take a quick second and review why that is. How about? If we look at a sum of squares, there's a couple of reasons for this. If I want to try to factor that, for one thing, look at the discriminant. The discriminant is going to be negative. If I look at the value of b squared minus 4ac, that's b is 0, isn't it? Right? A is 1, b is 0, c is 1. That's going to give me 0 minus 4 times 1 times 1, which is negative 4. And so the value under the radical in the quadratic formula is negative. What's that automatically mean? Imaginary, good. So non-real answer, so imaginary solution. There's one way to look at it. If you were, think about it in terms of a quadratic equation. If you were trying to find the zeros of this, because we know that the real zeros correspond to the roots, right? Is this kind of ringing a bell a little bit? If I solve this, I would get x squared equals negative 1, and that has, that can't work, can it? If I square root both sides, I'm getting i's again. So in this case then, you know that the bottom can't factor, and so there's no way we could cancel factors on this one, okay? So that's what we're stuck with. That's kind of ugly, but it still does the job. What if we wanted to know, let's say, we had this original function up here, this is our y. What if we wanted to know the value of the slope of the tangent line, or the value of the derivative? At x equals 3, what would we do? Yeah, I just plug it in, right? As ugly as that formula is, it's not a big deal to evaluate that function at 3. I just plug 3 in for x, right? So it's still going to do the job of a derivative, even if it is ugly. Okay? All right, so let's try one more of these. How about, like this. Say we have that one. Okay, now before we jump into this, and this is something I would strongly encourage you to do in calculus and probably like physics too, maybe analytical classes. Before you just jump in and start doing stuff, take a second to really think about this, because a little bit of time up front thinking about a path, eventually, that saves you a lot of time. Jumping in and doing stuff that's wrong can be frustrating and time consuming. So, what do you want to do with this? It's a quotient, right? So I got to use the quotient rule, but that's kind of an inconvenient way to write the top. Okay, we could write it as x to the negative 1. We could do some simplification with this. If we've got functions like this that I could turn into a rational function, meaning a polynomial on the top and a polynomial on the bottom, that's a good idea. I think I said this before, polynomials in calculus are our very good friends. They're really easy to deal with. Differentiating polynomials is a piece of cake. Multiplying polynomials is relatively simple. So it's generally a really good idea to spend a little bit of time up front before you do the calculus to pre-write this thing in a way that's going to make it easier to do the quotient rule. So this is similar to stuff we've done in the past. If we have a fraction on the top or the bottom, what was our strategy before when we were simplifying stuff to solve limit problems? Well, okay, we multiplied conjugate if we had, typically if we had square roots in there. We need to rationalize square roots. What do we do when we have a bunch of fractions? Yeah, we just simplified. We just got common denominators. We got one big fraction on the top, one big fraction on the bottom, flipped and multiplied, and turned it into a quotient of two big functions, right? So on the top here, we could turn that into one big fraction if we just got a common denominator. What would that be? X. So that means 3 is going to become what fraction? 3x over x, right. And so the top then is just going to look like 3x minus 1 over my common denominator of x, right? Yeah. Everybody agree? Okay. All divided by x plus 5. Okay. And so now in the past we've always written that as x plus 5 over 1 and flipped and multiplied. But you've probably seen a pattern here. If I'm multiplying, or I'm dividing, a rational function by a polynomial, all that ends up doing is whatever the factor is on the bottom, the denominator of the numerator, the x that's in our top fraction, it's just going to end up being multiplied by the x plus 5, isn't it? And so I would encourage you to kind of just make that jump algebraically. We want to trim the algebra down as much as we can. So we don't really need to multiply by 1 over x plus 5 to make that happen. We can see it's going to happen. And we know on the bottom then we're just going to get x times x plus 5, right? We'll give you a second to absorb that. Can you kind of see that one happening in your head a little bit? How we can skip that step, and then on the top we just get 3x minus 1. Okay? And that's better. That's a better way to handle it. And then on the bottom, here, one other issue. Now, if I were to leave the function like this, think what we're asking ourselves to do here. We're going to have a quotient rule, but the way it's written right now, the denominator is a product. So when we take the derivative of the bottom, that would involve the product rule inside the quotient rule. That sounds like a lot of stuff to do, right? How can we fix that easily? How can we avoid making the distribute? Sure. Yeah, just distribute. Much easier, right? Now we've rewritten that in a way that's just like the one we just did, right? That's no big deal. And we won't even do that one now. I mean, we just did one like that. That's not a big deal. Okay, some other issues come up. You tell me here. The game is quotient rule or not quotient rule. And our goal is, if we look back, to avoid the quotient rule like the plague, because the quotient rule was hard. The product rule was easy, right? So if we can make something into a product rule or while we're at it, let's write down the other game that we know. The derivative with respect to x of cu to the n, the power rule was what? Good. So both of those are much easier to do than the quotient rule, right? If we can avoid it, we should. So back to our game. Quotient rule or no quotient rule? It's a great game. Remains to be seen, I guess. Okay, if I want to differentiate that and find y prime, Is that a quotient rule problem or not? No. Aaron, a no, definitive no. You guys want to weigh in on this? What do you think? I could use the quotient, but why? Yeah, why do it, right? I mean, if I take for example u to be 5x to the fourth and v to be 8, what's v prime going to be? 0, right? So here's a rule: if we have something that looks like a quotient, but the bottom is a constant, it's not a quotient. It's just a constant times a power of x, maybe. Like in this case, I could pull the constant 5/8 out front and just leave it there, right? That's a constant. It's fraction, but still, it's just a constant. And then I've just got an x to the fourth, so it becomes a simple power rule problem, right? So unless the variable's on the bottom, we don't have to worry about quotient rule. Yeah. So y prime would just be 5/8 times 4 x to the third, which is what? 10, what was that? 28, so 10/4, so 5 halves, is that right?
Yeah.
Is that right? Yeah, 5 halves.
37 eighths.
Okay.
What? Wait, 4 times 8? What's 32? What?
Yeah,
It's 4 times 5.
4 times 5, so we can do a little cancellation here. We could do that, right?
Oh.
Does that make sense? Okay, how about this one? Quotient rule? Or no quotient rule? What do you think? What's that? Oh, nothing? Okay. Anybody want to weigh in on this one? What do we think here? Yes, sir. You have an idea?
Not a quotient rule, it's just 9/5 times 1 over x squared, which is really 9/5 times.
Perfect. Okay, so here's another way we can avoid the quotient rule. The quotient rule, of course, would work, but it would be unnecessary. I mean, just ample room to make a mistake. We can make this easier because I don't have anything on the top. My only variable is on the bottom. I could write this as a negative power and just fall back on the power rule, right? Way easier. So we could write this as 9/5 is my constant, x to the minus 2, and it looks just like the one we did, right? So what's y prime then? Good, negative 18/5 x to the negative 3. And if I want to write that in terms of a positive exponent, what is that? Yeah, good. Okay. So once again, we can avoid the quotient rule. All right. How about quotient rule or no quotient rule? What's the answer? Quotient rule. Yeah, we can't. Okay, so that one, yeah, gotta do quotient rule. Okay, how about this guy? What if we had, say, Looks like quotient rule. Can anybody see a way we could weasel out of the quotient rule on this one? Okay. I think now we know the -3/7 we can just pull out front. That's a constant, right? Okay. Now we could factor an x out of the top. Good, we could do that.
Oh, and they cancel.
Even if, now, let me make it, okay, so I'm going to see if I can foil you on that one. I'm going to change it a little bit. So we can factor an x out of the top and cancel, but let me change it so we can't. And I'm going to claim we can still do quotient rule. It doesn't factor. but we don't need it to. We don't need it to.
We can cancel.
Yeah. Okay, because now think about it this way. If I've got a common denominator, I can split that denominator among all the terms in the top, right? So I could write this as one fraction with a common denominator or three fractions, right? Now look at what each of those fractions is going to do. If I'm dividing powers of x by powers of x, I can use my exponent rules and just, subtract the exponents, right? And write those as single powers of x. And so there is a way we can manage to avoid it here too. I'm going to pull that -3/7 out front. Let's forget about that for now. And if I end up dividing the rest of this out, what's 3x over x? What does that simplify to? 3, yeah. What's -2x squared over x? Yeah. Right? -2x. And then finally, what's 5 over x, written as a power? Yeah. How about that? So there, too, we can avoid the quotient rule. Now this becomes one where we leave the constant out there, and I just differentiate each of these terms. No big deal. Right? That make sense? And then at the end, we'd have to distribute that -3/7, yeah. Okay? All right, so now there's a free extra bonus here with this that allows us to get some other trig functions pretty easily. Now, we only know 2 trig functions out of the 6 right now, right? So that's pretty bad. We need some more. But if we remind ourselves what those are, it's the derivative with respect to x of sine x, you've already told me many times, is cosine x, and the derivative with respect to x of cosine x is
Sine x.
okay, so how then could we do the derivative with respect to x of tangent x, do you think? What if we handle this? Yeah, what if we write tangent as a quotient? We now know the quotient rule. So that's equal to the derivative with respect to x of sine x over cosine x, right? And so by the quotient rule, what's that give us? Okay, good, bottom, so cosine times, derivative of sine is cosine, okay, minus sine times negative sine all over cosine squared. Right? Okay, so if I simplify that, cosine times cosine minus sine x times negative sine x. So sine times sine is sine squared, but I got negative times negative positive. And what is that? That's 1. Yeah, that's our Pythagorean identity for trig functions, right? We know that sine squared theta plus cosine squared theta always equals 1. So we can write the top as 1. And now 1 over cosine squared. Wouldn't you agree that's the same thing as the quantity 1 over cosine x squared.
Yes.
And what's 1 over cosine x? Secant, yeah. So how about that? We've got a new trick. We now know that the derivative with respect to x of tangent x equals secant squared x. Okay. And we could do the same kind of thinking, and I'll just give you the rest of them, and come up with, using the same patterns, we could come up with the other trig functions. We know that the derivative with respect to x of cotangent x equals, what do you think? What's your intuition tell you about that one? Negative cosecant squared x, that's right. There's a real symmetry with these trig functions, right? I'm going to give you secant x and see if you can tell me what cosecant x is. The derivative with respect to x of secant x equals secant x times tangent x. So what is the derivative with respect to x of cosecant x, do you suppose? Almost. Cosecant x times cotangent x. There's one little piece we're missing. Negative, yeah. Now look at the pattern here. If we organize these, let me organize these on a different page, and this will make it easy to remember how these things work. We can look at sort of what we might call the normal trig derivatives and then the co-trig derivatives, the co-equivalents. So we've got, if we line them all up, the derivative with respect to x of sine x, the derivative with respect to x of tangent x, and the derivative with respect to x of secant x, right? Let's compare those on one side to the co-alternatives on the other side. Okay, notice what happens. The derivative with respect to x of sine x is cosine x, right? So the derivative with respect to x of the co-alternative of sine, the cosine, is going to be the equivalent cousin function of cosine, which is sine, but with a negative sign out front, right? See how that works? So we end up over here with a negative sine x. Cosine pairs with sine. So if I know, in other words, if I know this one's a freebie. I can predict what the outcome's going to be. It's going to be the other cousin of cosine is sine, but I got to put a minus sign in front if I'm taking the derivative of cosine, right? How about tangent? Tangent, we said secant squared. So cotangent's got to be minus the cousin of secant is cosecant squared, right? So it's 6 for the price of 3. You know the 3 normal ones, you can predict always the other degree. Derivative of secant, we said, is secant x, tangent x, so we got to have the opposite of the cousins of those. Whoops, cosecant x. Cosecant x, cotangent x. Right? Make sense? So, okay, so last problem today. Let's finish out strong. Let's try this one. What if we have y equals that product? Find y prime. Okay, what do we got?
No, it's like X squared.
X squared, okay, good, times derivative of tangent is secant squared. Okay, and so if we wanted to clean that up, I guess that would just look like what? Well, one thing we could do. What would I do to this one over here?